Hello and welcome to this short video lecture on the first part of tissues, which is epithelia. Now, with epithelia, we're going to look at the properties, and then we're going to consider the shapes which give the epithelia its terms or names, and also the layers of thickness that epithelia has. So let's get straight into it. So, tissues, epithelium. Now, epithelium essentially means to line or to cover an organ cavity, or the surface of the body, for example. In general, epithelia create membranes. So when we're talking about a membrane, we're talking about the epithelial tissue. So if it's lining and covering all of our body organs, all of our cavities, and also on the outside, meaning our skin, this is also epithelia, then it's going to have a series of properties associated with it. Now, some will depend upon the thickness and some depend upon the shape, and we'll get to that in just a minute. So other properties that you'll find with a lining membrane or a covering membrane is that it's avascular. Now, avascular simply means that it has no direct blood supply. That seems a little bit counterintuitive, because this is a lining, it's covering, it's a membrane, it surely must have blood supply, because that indicates that it's receiving oxygen and nutrients and able to get rid of waste products. These are living cells after all. Well, in most cases they are living cells. In certain specific cases they are not living cells, and we'll get to that in a little bit. So avascular simply means no direct blood supply. It doesn't mean it doesn't have any access to the blood at all. And always with an epithelia, you will have a connective tissue layer sitting right below it, literally connecting it on to whichever cavity or organ it happens to be associated with. The connective tissue layer will have a blood supply, and it will leak from the connective tissue layer into the epithelia, and that's how the cells gain their nutrition and get rid of their wastes. In most cases. Right, so we have, if no blood supply, it lines and it covers. It can be protective, but it can also allow for rapid diffusion. Now, those both seem to go against each other, and that's because we have different types of epithelia. One is designed more for protection, like a wall stopping stuff coming through, and another one is designed really more for to be very, very thin, but still have some shielding there, but still allows for very fast transfer through it. So, to explain these, we really need to look at the types both by shape and by their thickness. Now, by shape there are three main types, and by thickness there are also three main types. So starting with shape, we have squamous, cuboidal and columnar. Now these are shapes, so hopefully if I say the word squamous, you're going to think of the term squashed, because that's exactly what they are. They're completely squashed. So to give it some sort of a shape here, in squamous, meaning squashed, the cell is flattened down. If you think of it like a paving stone, really. So this is a very thin cell. This is the nucleus. So in squamous, the cell is so flattened that the nucleus is actually sticking out of it. So this makes it very, very thin, and it allows things to pass through it very, very easily, because it's very, very thin. And so you'll find squamous in places like the lung tissue, because it allows rapid movement for the gases, oxygen coming in and carbon dioxide leaving. So, next one, cuboidal. Cube. So, not flattened, this is now cube-shaped. Another giveaway of cuboidal is a central nuclei. So again, different, just one layer. So in the cuboidal, we still have just one layer, if it's a simple cuboidal, which we'll get to in a little while. But it's wider, so it can actually do a slightly more chemistry inside the cell to try and control what's moving through it, and that's an important difference between the two. So in squamous, this is just free diffusion. If there's a stronger, higher concentration this side and this side, and it can pass like oxygen, it will just move through. The same true for the carbon dioxide going in the opposite direction. It's higher here, lower here, it just diffuses across. There's no energy, there's no real chemistry going on there in that case. However, in a cuboidal, you can actually have, let's put a different colour in here, you can have a special gate which acts as a pump. And this is the sodium-potassium pump, and they're very, very common in our bodies. And so on this side it can be pumping sodium out, and therefore inside it's dropping the sodium concentration. And if we have a tubule here which has got a high concentration of sodium, and the brackets around the sodium just really mean concentration of, so it's got a high concentration of sodium. This has got a dropping concentration of sodium. Because it's being pumped out here, it can draw sodium in from this tubule, which happens to be a nephron in the kidney. So this is where the ultrafiltrator, once the fluid comes out of the blood, enters into the nephron, will eventually become urine. This is how we get the fluid and the salts back, by a little pump here, dropping the concentration here, pulling through sodium, and then allowing, and then the sodium gets pumped out here. So you're getting this conveyor belt of sodium moving out of here to here to here, all because of this square shape of the cuboidal that allows for a bit more chemistry to take place. So it creates concentration gradients using active transport. Now that's something that we haven't really got into in a great deal of detail. I know we talked about it in the last week's work. If we're doing essentials, of course if we're doing anatomy, then you do it in physiology. Don't worry too much about this stuff. This is just an example to show why the square shape really helps, but hopefully that helps you think about the cuboidal being square shaped, having a central nuclei, and allowing for passage of electrolytes through it, but actually being selective in how it does it. Anything that can diffuse through this will diffuse through it because it's so thin. This is a little bit more selective. So now we have the columnar. Now the columnar, very tall, have a lot of distance between the top and the bottom area of the columnar. Again, in a simple layer, it still allows passage of things to go through it. However, it can store things inside it. It's big enough to store stuff. So if this is the gut, and you've got to bring in nutrient, it's got to get through this cell and get to the other side of the cell where we have the blood supply and also the lymph vessels. So whatever's coming through the gut has to pass through this columnar cell and get into the blood, into the lymphatic system. Because it's big enough, again, it can actually act as a store, and these cells don't have a very long life, so they can be sloughed off and lost in the fecal matter of the gut. So if too much is coming in here, we can have a mechanism by which at this end it can stop it from entering the blood itself, hold it here and slough off. So all three types, the squashed, the square and the column shaped, are lining cavities. In this case we're lining the lung tissue, in this case we're lining the kidneys and the nephrons, and in this case we're lining the gut. But they all allow for things to pass through them, but because of their shape they allow a different type of passage or a different control level. So very little control but very fast diffusion in squamous. In cuboidal there's still quite a fast transfer, but it's now a little bit more chemistry dependent, so it's now creating gradients etc. for things to move. And of course in the columnar, because it's got a long way to go from bottom to top, then there's even a capacity to store things inside the cell for a period of time, potentially even stop it from entering into the body proper. So that's our three types of epithelia: squamous, cuboidal and columnar. Now we need to consider the final part of it really and look at the layering of it. So layering can be simple, which equals one layer. So if you have one layer of squamous, it is simple squamous. If you have one layer of cuboidal, simple cuboidal, one layer of columnar, simple columnar. Now in all of these three examples I've given you, all three of those were simple, meaning they just had the one layer of cells. And if you're looking at passage, then that's what you want. You want one layer, because any more than that interferes with the ability of things moving from one side to the other. So that gives us stratified. Stratified means layered, greater than one. So 2 and above would be a stratified layer. Now stratified layers of squamous, well, that's our skin, is keratinized stratified squamous. This is very thick and very protective. Inside our cheeks is stratified squamous. It's non-keratinized, so it's not the same as our skin in terms of its feel and texture, but it is the same cell type. But it's many layers of squamous cells on top of each other. So in a stratified squamous, I'll put it on this side, you'd have these flattened cells, but you'd have lots and lots and lots and lots. So you're building up a big barrier. So stratification of the layers immediately takes it from allowing from diffusion and active transport to protective. So protective really equals a stratified layer. There is some protection in simple layers, but it's not its main function. And for rapid diffusion, you have simple, and in brackets, pseudo-stratified. Now I apologise, my writing is never the best, but hopefully as I'm saying the words you actually recognise what the word is. So simple, one layer; stratified, greater than one layer, and for protection. So a lot of our body membranes, such as our skin from our integumentary system, is stratified, in this case stratified squamous. Very, very good protective layer. Most of our mucal membranes, where we open out to the surface, are also stratified squamous. So again, very protective. So we have this last one to look at, the pseudo-stratified. Now, the word pseudo means that it looks like something without being it. So pseudo-stratified really just means it looks stratified, but actually it's simple. So if I draw this out, the classic example is of pseudo-stratified columnar. So if we draw a standard columnar, let's do this. So it would tend to look And you'd have your nuclei. They tend to sit toward the bottom of the cell. So that would be your simple columnar. Now compare that to a pseudo-stratified layer. Alright, now this is also columnar. And this is now referred to as pseudo-stratified. Why? Because it's very crushed together. When it crushes together, instead of being a columnar shape, the cell tends to get squashed into a wine bottle shape. And when it gets squashed like that, it pushes the nucleus into the wider part of the cell. So for some of these, that's at the bottom, and for some, it's been squashed at the bottom, so they're at the top. So now when you look at it under the microscope, it looks like you've got one layer here and one layer here because of the way you're seeing the nuclei arranged. In actual fact, you've just got one simple layer. Because here's one side of it, the basal side, say, and then going all the way to the top, this cell here reaches the other side. So that is one layer. If you've just got one cell that makes it from one side all the way to the other side, you have a simple layer. If it looks like, because it's been crushed and you've got the two layers of nuclei, like there's more than one, even though it is one, it's referred to as a pseudo-stratified layer. So a pseudo-stratified layer is essentially a simple layer that just looks stratified without being it. So we really have sort of just the two, simple and stratified, with this complicating factor in the middle. For the ease for us, the only pseudo-stratified layer that you will come across at this level is pseudo-stratified columnar epithelium. And in general, they are all ciliated. So they have a little fuzzy border at the top. Now it's not the only epithelial type which is ciliated, but we try and keep it simple at this level so that when you're thinking about it, if you see cilia, you can think of pseudo-stratified columnar epithelia. As you get the feel of it, it's quite a long name. Ciliated pseudo-stratified columnar epithelia is a bit of a mouthful. However, so that's how we name them. Simple, and then which shape, stratified, which shape, and then the pseudo-stratified. There's another type called transitional, which includes a stratified layer which includes all three types in it that look like all three types, and it transitions, and this is what we find in the bladder, because the bladder starts very small and then stretches out as it fills with urine, and so it starts looking sort of very squarish and columnar, and it gets stretched out and looks very, very squamous, gets very squashed. So that's us for epithelium. I hope that helps you in your understanding, and obviously ask me if you require any help. Otherwise, we'll take a short break and we'll come back and we'll discover a little bit about the connective tissues.